In this video we answer some of Professor Canning's questions in a little bit more detail about isotopic pyrolytic carbon. It's relevant because it gives my new heart valve that's been put inside me a lifetime of 10 million years. In this view we've stripped away everything except the atriums which prime the heart and the aorta and arteries which store pressurized blood, and also the coronary arteries and veins which you can see around the outside. The arteries supplying my heart were good except for a single point blockage caused by stress, and this was fixed up when they cut me open to replace my valve. We're in the left ventricle, which gets primed with blood through the mitral valve which you can see opening and closing off to the right. Directly in front we have the aortic valve which holds back high pressure blood, but it opens when the ventricle compresses blood to sufficiently high pressure. I only had a 2-part rather than 3-part valve, and over the years it wore out, neither opening fully nor closing properly. They simply cut it out and sewed in a mechanical valve. If we zoom into the wall, we see it's made out of a black shiny material. For thousands of years we've been getting carbon from oxygen-starved fires and calling it charcoal. Nowadays, if we get the temperature right, use about 15% propane and helium, we can make isotopic pyrolytic carbon. This picture shows a three-dimensional jumble of crystals pointing in different directions. In the microscope picture off to the left, you can see different grain boundaries showing the orientation is different in different areas of the pyrolytic carbon. The area to the right is magnified a further 200 times, and through electron diffraction we can tell that the substance we're looking at is actually not graphite but something a bit more disordered. If it was graphite, it would have this beautiful pattern of spots. If we look more closely, we can see that the layers are wavy. This means the material cannot crack, but it is also flexible. Being very hard but flexible and not being able to crack means the material can last a very, very long time. What's hard to imagine is that at these very high temperatures, the carbon molecules must be tumbling. How then do they actually slow down and actually form carbon layers? To visualize the problem, imagine one of these tumbling pieces of chocolate is a carbon molecule. How does it stop tumbling to lock into place?